When talking about coordinates in three-dimensional space and vectors in three-dimensional space, there are a lot of similarities between this and two-dimensionality, which would be like a Cartesian plane. So when we're talking about space coordinates, we're talking about three-dimensional. And so if we think about the two-dimensional definition of distance here, so we have our xy plane, and we have 2 points in that plane. Then the distance between those 2 points would be that straight line, the length of that straight line, or that straight line distance here. And so to find that, we can do Pythagorean's theorem to find the length of that line. And so when we talk about the distance then of that line, that being the hypotenuse of the right triangle, then we're talking about squaring the sides and square rooting them, so you can kind of see the analogy here. In 2 dimensions, we would have this as the distance formula, which is nothing more than Pythagorean's theorem. And so in 3 dimensions, we just add a z-coordinate and find the length in 3 dimensions. So if we solve that then and eliminate the radical, squaring both sides, we're talking about all of those points that are away from one particular point. So if we start back up here at this particular point, and we in two-dimensional space, and we take all of the points that are that distance, the length of that red line away, we get our circle. Well, if we do that in three dimensions, then we'd get a sphere. So here is the equation of a sphere then. It looks a lot like the equation of a circle. It's just that, we've extended it for 3 dimensions. This is, again, notice the similarities. This is nothing more than Pythagorean's theorem. That's an old Pythagorean's theorem. There we go. So then, as we're talking about then, the distance between 2 points, then we can start talking about vectors. So vectors we have a component form here. We just add a z component here. This is a component in the z direction. Same with this, it's just a component in the z direction. And then we define everything as we did, again, in 2 dimensions. So we have the length of a vector. There's your distance formula again. We have the unit vector. Addition is the same, scalar multiplication is all the same. So just going through some basic plotting of points. Typically what we do is we draw the z-axis as the vertical axis. So x and y are like you would have if you had this paper sitting on a tabletop, and then the z-axis would be coming right out of the top of the table, so straight out towards you. So if we kind of try to give you a visual as to what that's like, we'll take this grid. Let me just copy it and paste it here. And so if we're talking about a tabletop here, here's your desk. So here's the desk you're sitting at. Then we would take this and we would, spin it so that the y and the x-axis were, laying down on your tabletop. So there's your x-axis, there's your y-axis, and your z-axis would be coming straight out towards you. And so if you notice, here's the positive x, here's the positive y, and here's the positive z. So so this positive x and the positive y, this makes the first quadrant. So it would be kind of like if you had your tabletop here and this was your positive x, and this is your positive y, and then your z would be coming straight out towards you, straight out of the screen, so to speak. So when we talk about these coordinates x, y, z, we're talking about 0 in the x direction, 4 in the y direction, and -5 in the z direction, which would be down. So 0 and then 4, 1, 2, 3, 4, and then down 5 boxes. So 1, 2, 3, 4, 5. So there is that first point. The second point then for 0, 5 is you would look at that as 4 out in the x. So positive x, 1, 2, 3, 4 along there. It's not going in the y direction, so we're not coming along the along this direction here into either of these quadrants. And then we're going up 5. So we're counting straight up vertically, 1, 2, 3, 4, 5. So there is your 4, 0, 5. So if we can picture this as, you know, this XZ plane as like the wall, then we just went along the floor and up the wall, but not into the classroom, sort of thing. So there are those 2 points. So if we practice then this one in terms of planes, it says find the coordinates of a point 7 units in front of the YZ plane. So the YZ plane is right here. And so if we're in front of that, that means we're out here. That's the x coordinates. So this is your x coordinate of 7. It says 2 units to the left of the XZ plane. So here's the XZ plane. And 2 units to the left would be back here in the negative y direction. So here is our negative y. So here's our y of -2. In front of this would be our x of 7. And that 1 unit below the YZ plane, so the YX plane. So the YX plane would be like your tabletop, and we're 1 unit below or underneath the table. So that would be, then that would be our Z, that would be a -1. So we're looking at 7, -2, -1. So out 7, 1, 2, 3, 4, 5, 6, 7. Back 2, so 1, 2. So right here, so that you can kind of picture that as being on your tabletop, and then we're going to go below the table by 1, so we're going to be right there. So we're kind of, if this is our tabletop, then we're underneath the table. So there's that point in the 3-dimensional plane. So this is, we're going to make a triangle in the 3-dimensional plane here. So we're at 5, 3, 4. So we've got 1, 2, 3, 4, 5, out 3, and up 4, 1, 2, 3, 4. So that gets us right there. So there's 1 point. So you can kind of see how we came across and over and up. So, you know, to get the 3-dimensional look to this is a little tough. And then the next point, 7, 1, 3. So out 7, so that's 5, 6, 7. 1 in the y direction, 3 in the z direction. So 1, 2, 3. So again, over and then in the y direction and up. And then we have 3, 5, 3. So we have over 3, 1, 2, 3, out 5, 1, 2, 3, 4, 5, and up 3, 1, 2, 3. So there's the third point. So we have these three sides of this triangle, and with 3-dimensional coordinates, it's really hard to tell how long the sides are because we have this, you know, we have this distortion of trying to represent a 3-dimensional object in a 2-dimensional world. So we have to figure out the length of each one of these. So, so we'll just call this point A, and it was the last one, so we'll call that point C, and call that point B. So this was B, this was A, and this was C. So we have to find, you have to use the distance formula to find that. So we're going to find the, we'll find the distance from A to B. So we'll go ahead and set up the distance formula for that. So we've got 7 minus 5 squared, so 7 minus 5, 1 minus 3, and 3 minus 4. Okay, so there's the distance from A to B. So we're looking at 2 squared. This is a negative 2 squared. And don't forget, when you square a negative value, you get a positive value, because we're squaring the negative and the 2, and we get negative 1 squared. Again, getting a positive value here. So we've got 4 plus 4 plus 1. Whoops. Plus 1. So the distance from A to B is the square root of 9, which is 3. Okay, so let's look at the distance from B to C. So if we take a look at B to C, we're going from B to C, so we'll go 3 minus 7, 5 minus 1, and 3 minus 3. So if we take a look at this, we can see that the z distance is 0. So from B to C, yeah, if we take a look at this, B and C are up at the same elevation of 3. So we went up 3 from the desktop here, we went up 3 from the desktop here, so this line is actually parallel to the desktop. So we got minus 4 squared, that's 16. We have 4 squared, that's another 16. That's a square root of 32. So definitely not 3. So we know that this side is, let's see, the square root of 32 is bigger than 5, so we know this side's longer. And let's look at the distance from C to A. So looking at C to A, we're talking about from here to there. So we've got 3 minus 5, 5 minus 3, and 3 minus 4. So looking at that, it looks like we have the square root of negative 2 squared, which is 4, 2 squared, which is, again, 4, and negative 1 squared, which is 1. So it looks a lot like that one. So we know that the distance here is 3. So we've got two sides that are the same length here, these guys right here. And so this triangle has got a side that's parallel to the tabletop, and then this point that kind of comes up a little higher. So we have two sides the same length, so we definitely have an isosceles triangle. So in this question, we want to find the midpoint between 2 points. So we have 4, 0, negative 6. So the first point is over in the x direction 4, 1, 2, 3, 4, and not out in the y direction at all, and down 6. So 1, 2, 3, 4, 5, 6. So we talk about the XY plane being our desktop, so we're beneath the desktop, but just below that x-axis. And so we'll call that point A. There we go. Okay, and then point B is 8, 8, 20. So we come out 8, we go 1, 2, 3, 4, 5, 6, 7, 8 in the x direction. Then we gotta go in the y direction, 1, 2, 3, 4, 5, 6, 7, 8. So visually, we are looking like we're lining up with the z-axis, but we're really not on the z-axis because we moved out from the z-axis and then up in the y direction. So we're kind of out here in their tabletop in front of the z-axis, which is coming right out of the desktop. And then we gotta go up 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Just made it in. So there is point B. And so what we want to find is we want to find the midpoint between those 2 points. So if we go ahead and draw that line there, there we go. So we go ahead and put that line right in there. So we want to find the point that's right in the middle of that line. So really we want to find this distance that's halfway between 4 and 8, halfway between 0 and 8, and halfway between -6 and 20. And so if we want to find a point that's halfway in between, algebraically, all we really have to do is average those things. So if we think about it, we were out 4 for point A, and we're out 8 for point B. Halfway between those things must be 6. So for the x component, for the x component, 4 plus 8 divided by 2 gets us 6. For the y component, if we think about it, we're up 0, and then on point B we're up 8, so we're up 0. Then we go up 8, so we must be out 4 here. So 0 plus 8 divided by 2 is 4. And for the z component, for point A we start down 6. For point B, we're up 20. So if we think about that, the fact that the vertical distance between these 2 points were 6 below the tabletop, and this one we're 20 above the tabletop, they're 26 apart, basically. So we've got to find the midpoint. And on a number line, if you think about that, that's going to be on the positive end of 0. But if we take -6 plus 20 divided by 2, that's 14 divided by 2, that's 7. So if we think about the midpoint being 7, the distance between the points being 26, then 7's got to be 13 away from 20, and it is, and 7 is also 13 away from -6. So that's the middle of the rise, so to speak. So our midpoint's got to be 6, 4, 7. So if we count out 6, 1, 2, 3, 4, 5, 6, and then in the y direction 7, 1, 2, 3, 4, 5, 6, 7, and then up. Oh, I counted that wrong. In the y direction 4. Let me back up. So out 6, 1, 2, 3, 4, 5, 6. Y direction 4, 1, 2, 3, 4, and then up 7. 1, 2, 3, 4, 5, 6, 7. There's the midpoint of that line segment. This is kind of similar to what we were doing in the previous chapter, and that was rewriting things to identify what conic section it is. And we're just going to do this in 3 dimensions here. So we want the standard form of a sphere, and the idea in standard in the standard form of the sphere, the idea here is that this will allow us to pick out the center really easily. And so we need to set this up for completing the square. So we're going to group our terms together. So we have our x squared plus 9x, and then to complete the square we need a perfect square trinomial there. And then we have our y squared minus 2y, and likewise we need a perfect trinomial there, so it can be factored. And then we need our z squared plus 10z, and our perfect trinomial there. And this is the odd one that doesn't have a variable, so we're going to push that to the other side as a -19. And then we're going to go ahead and complete the square. So 9 divided by 2, and then square that. That's what needs to go here. So this is 81 over 4. And -1 divided by, or excuse me, -2 divided by 2 is -1, and then we need to square that. So we get a 1 here, and then 10 divided by 2, which is 5, and then we got to square that, so we have a 25 here. And so what happens is we just added 81 over 4, and we just added 1 and 25 to the left side, So we're going to have to add all of that to the right side as well. So making this perfect square trinomial here, factoring that, that's going to be an x plus 9/2 quantity squared. This is going to be a y minus 1 quantity squared. This is going to be a z plus 5 quantity squared. And then we have a little bit of math to figure out here. So we have 26 minus 19, that's 7. I'm going to write 7 as 28 over 4. And we have plus 81 over 4. And so this ends up being 109 over 4. And so we have a center of, and we need to get this in standard form. Let's talk about that, which means x minus and y minus and z minus. So if we have to rewrite it in terms of standard form, it would look like double negatives everywhere we see a positive. And that reminds us that the center is actually a negative value here. So that helps us with that. And this is the radius squared. So the square root of this is just the radius. So we have a center at minus 9/2, comma 1, comma minus 5. And we have a radius of the square root of 109 over 2, just square rooting the bottom. If we take a look at the next example here, it says find vector z such that vector z is this minus this plus 2 of these. And so since they are in component form, we can just add them real quickly if we add like components. And the 2 and the minus sign are just scalar multiples. So we're going to add 1, 2, 3, and we're going to subtract 2, 2, minus 1, and we're going to add twice 4, 0, minus 4. And so, like I said, since they are all in component form, we can take the x components of each and add them together, the y components of each, add them together, and the z components of each, and add them together. And so I'm going to do that all in one step here. So here are my x components. I've got 1 minus 2 plus 2 times 4 is 8. So there's my x component. My y components are going to be 2 minus 2 plus 2 times 0. So that's 0. And then my y components, or excuse me, my z components are going to be 3 minus a negative 1, which is plus 1. And then the last one is 2 times negative 4, or minus 8. So vector z then looks like, when we do the math here, this is going to end up being minus 1 plus 8, which is 7. This ends up being 0. And this ends up being 4 minus 8, which is negative 4. When we talk about parallel, being parallel, we know that being parallel means we go over and up the same amount on a two-dimensional Cartesian plane. So the idea of parallel then in 3 dimensions is making sure that we go up and over, and out and over and up, I guess you could say, the same distance. And so if we think about then the vector form here, we've got 2 vectors. We've got vector 7, 6, 2. So we're talking about 7 in the x, 6 in the y, 2 in the z. So if we draw that, it would look like, I'll just draw it starting at the origin. So 2, 3, 4, 5, 6, 7, 6 in the y direction. So 1, 2, 3, 4, 5, 6, and 2 in the z, 1, 2. So here's the terminal point. Here's the initial point. And excuse me, if I would draw a vector in that direction, then that vector would look like that. Not quite sure why I didn't have an arrowhead there. Let me try that again. There we go. The vector would look like, there we go, that. So there's the vector 7, 6, 2. And so anything that is parallel to that then is going to go over that much, out that much, and up this much, or a multiple of that. So if I went 14, 12, 4, if I could go out 14 and then 12 and then 4, it would again be parallel to that. It would just be longer. So what we're looking for is something parallel to this, or possibly something parallel to this. So if we look at this as its own vector, so let's see here, let's change colors. So if we're looking at 14, 16, negative 6, which is too long to do on the grid that I have, something parallel to that would be 7, 8, minus 3. So I just made something that was half as long. So I can do that. I can go, I think, out 7. So 1, 2, 3, 4, 5, 6, 7, and then up 8. 1, 2, 3, 4, 5, 6. I do go off the grid. 7. And 8, and then down 3. So 1, 2, 3. So there would be the terminal point of that vector. There would be the initial point of that vector. And if we drew that vector, then that would look like that. And so those are the two things we want to be parallel to. So considering that, let's take a look at these 2 points. We've got 5, 4, 1, so out 1, 2, 3, 4, 5, over in the y direction 1, 2, 3, 4, and up 1. So there's our initial point. And then our terminal point is negative 2, negative 4, 4. So negative 2, 1, 2, negative 4, 1, 2, 3, 4, and then up 4. 1, 2, 3, 4. So there's our terminal point. So if we draw that vector, it's going to start here, and you might already be able to see which one it's parallel to, and it's going to end there. So it does not look, definitely doesn't look parallel to the red one, but it does look like it might be parallel to the green one. It's pointing in the opposite direction though. So if we take a look at this and write this in vector form, then that vector is that the x, y, and z components of that vector are going to be 5 minus a negative 2. Let's see, this is the initial point. So this is the initial, and that's the terminal. So I have to do terminal minus initial. So minus 2 minus 5, minus 4 minus 4, 4 minus 1. So there's that blue vector. So this is a minus 7, a minus 8, and a 3. And so if you notice, this vector is this, which happens to be a scalar multiple of the original green vector that we didn't have the room to draw. It just would have been twice as long. So this one must be parallel to 14, 16, negative 6. So some people might call this anti-parallel because it's pointing in the opposite direction. It's 180 degrees out of sync or out of phase, so to speak. This is pointing this direction, and the green vector is pointing that direction. So, so some people might actually term this as anti-parallel, but the idea is that the scalar multiple is a -2. So that's what turned that vector around. The idea of collinear then really comes from the concept of parallel. So if we think about 3 points that are collinear, and let's just talk about the two-dimensional plane right now, then if we would draw a vector from one point to the next point, these points a little bit bigger, and then we would draw a vector from one point to the third point, even if we didn't choose those 2 points, but maybe we chose these 2 points, you can see that if I have collinear points here, then any vector I draw between these three, from one point to the other point, even if I would draw them in the other directions, these would all end up being parallel vectors. And like I said, I could draw either the red one, the blue one, or the green one. It doesn't matter. If these points are collinear, these vectors are parallel. So all we really have to do is take a look at these points and set up 2 vectors and see if those vectors are parallel. So we'll take this first point here, 0, 0, 0, and we'll take this next point, 1, 3, -2. So over 1, out 3, 1, 2, 3, down 2. So there is the next point. I'm actually going to make those green. There we go. And so there's our next point. And then the last point, 2, -6, 4. So out 2, back 6. 1, 2, 3, 4, 5, 6. And up 4. 1, 2, 3, 4. So there's the third point. So if you look at these, I mean, you can kind of see that if we start drawing a straight line from one point to the next, or from that first point to that point, that if I try to connect 2 of those points, let's try to connect the 2 that are the farthest away, that last point, or that red point, certainly doesn't look like it lies on the line. So I would say that, you know, we're kind of giving you the impression that these probably aren't collinear. So let's take a look at some vectors. And it's easiest to make a vector from this point, since this point's 0, 0, 0. That seems the easy thing to do. So let's do, we'll call the first one vector v. And we'll use points A and B to make that. So vector v is going to look like 1, -0. There we go. Vector v is going to look like 1, -0, 3, -0, -2, -0. So vector v looks like 1, 3, -2. Oops, wrong bracket there. 1, 3, -2. So that's this, you know, vector right here. And then we can take a look at vector w. Let's call it. Let's pick more difficult ones. Let's make w out of A, B, and C. So we get 2, -1, and -6, -3. And 4 minus a -2. So this vector from B to C, so that would be right here from the green to the blue, looks like 1 and -9 and 6. So from B to C we go over 1, we go back 9, and we go up 6. And so if we look at this, we can already see that the first vector is out 1, and then these 2, so if the first vector is the same, these should be the same, and these should be the same, and they're not. So these are definitely not parallel. In other words, there is no way I can take a scalar multiple, whether it's like a 1 or a 2 or a 3 or a 4, or a half, you know, a fraction, is also a scalar multiple, and get these, and with these numbers, and get these numbers. In this example here, it says find the unit vector u in the direction opposite of u. So we're talking about if this is u, and I didn't put a grid here, but if we are over 6 and out 0 and up 8, then if we're in the opposite direction, then instead of, if I just kind of borrow this grid up here, if we go over 6, out 0, and up 8, the opposite direction would be reversing all of those. So instead of this way 6, we're this way 6. Instead of up 8, we're down 8. So we're -6 and -8. That would be the opposite direction. So that really is what that means, is that we're really talking about a negative vector u. And so our negative vector u would be -6, 0, -8. That's the vector u in the negative direction. And so if we want the unit vector, then unit vector means we have to take that vector and divide it by its magnitude. So magnitude is nothing more than distance. So the magnitude of vector u then is going to be the square root of all of its components squared. So we're going to have -6 squared plus 0 squared plus -8 squared. And so we've got then the square root of 36 plus 0 plus 64, which is the square root of 100, which is 10. So we know that the length of that vector is 10. And so the unit vector then looks like the unit vector in the direction. So let me kind of just clarify here. We talked about opposite direction because this is setting us up for part B. So the unit for part A then in the same direction as u would be then taking 6, 0, 8 and dividing it by its length, which is 10. So we're talking about then 6 over 10. We could reduce that if we want to. 0 and 8 over 10. Would be that unit vector. Then the unit vector in the direction opposite of u would be then taking that opposite u or negative u vector and dividing it by its length, which is still 10. Length is length. It's always positive. And so we have -6/10, 0, and -8/10.